Here is a combined summary of pages 1 and 2. This paper explores the potential of large language models, specifically GPT-4, in scaling evidence-based instructional design expertise. The authors aim to bridge the gap between theoretical educational studies and practical implementation, emphasizing the need for human oversight in ensuring the quality of educational materials generated by AI-driven language models. The research presents two detailed case studies where GPT-4 was applied in creating complex higher-order assessments and active learning components for different courses. The incorporation of large language models in learning engineering offers benefits such as personalized content generation, augmentation of existing learning materials, and support in evaluation processes. However, the reliability of GPT-4 can be inconsistent, particularly in complex subject areas, leading to potential inaccuracies and biases. To ensure high-quality learning experiences, a balanced approach combining AI-generated content with human oversight is essential. Previous research has explored the application of large language models in educational settings, such as generating questions or providing hints, explanations to students. However, the current literature does not extend beyond the creation of single-step open-ended or selected response questions. The author's work explores the application of GPT-4 in the development and assessment of educational content, revealing valuable insights into the potential benefits and challenges associated with using GPT-4 to automate the creation of higher-order assessments. The two case studies presented in this research illustrate the potential of GPT-4 in enhancing courses by incorporating active learning components for students. The first case study involves a course called E-Learning Design and Principles, where the instructor's objective was to address 30 instructional principles outlined in a specific learning objective. The second case study involves a course on computer systems, where the instructor's objective was to assess students' understanding of complex concepts. The research provides best practices for effectively using LLMs in instructional design tasks, such as utilizing templates, fine-tuning, handling unexpected output, implementing LLM chains, citing references, evaluating output, creating rubrics, grading, and generating distractors. The authors also share their vision of a future recommendation system, where a customized GPT-4 extracts instructional design principles from educational studies and creates personalized, evidence-supported strategies for users' unique educational contexts. The research focuses on the effectiveness of instructional principles, particularly the spatial contiguity principle, using a scenario-based predict-observe-explain (PO) method. A case study on the worked example principle is detailed, involving several days and iterations to finalize an example. This process was automated for other principles using one-shot prompting. Key aspects include generating assessments in the form of predict-explain, observe-explain scenarios, focusing on boundary conditions, and creating feedback for multiple-choice questions and short answers. The study also highlights the efficiency gained by automating the process, reducing the time required for subsequent principles by more than half. Additionally, a case study on learning analytics and educational data science is discussed, focusing on implementing a predictive model using Python and leveraging data visualization problems. The use of GPT-4 for generating content is explored, including strengths and limitations. The research emphasizes the importance of evidence-based guidance and the value of automation in educational content creation. Here is the combined summary. In the development of educational content, the authors leverage the capabilities of GPT-4 to design practice activities for students to learn predictive modeling in Python. Figure 2 showcases a segment of a Jupyter notebook, where students are tasked with writing code to identify at-risk students using predictive models. The authors employed a few-shot prompting strategy, which yielded better results compared to one-shot prompting. Notably, GPT-4 did not generalize the Altair library in the output Python code, despite all examples featuring it. Drawing from their experiences, the authors propose best practices for instructional design when utilizing large language models like GPT-4. These guidelines aim to maximize benefits while mitigating potential challenges. Firstly, utilizing templates for instructional design tasks can improve the quality of generated output, particularly for complex tasks involving specific instructional design principles. Secondly, fine-tuning for novel instructional problems can be achieved by adjusting the temperature value in the prompt to control the focus on knowledge components. Thirdly, handling unexpected output can be addressed by defining explicit rules in the prompt or using a lower temperature for output similar to input. Fourthly, implementing LLM chains for multi-step instructional tasks can improve output quality by breaking down tasks into smaller subtasks and combining them once quality is established. Lastly, citing references in AI-generated instructional materials enhances accuracy, credibility, and simplifies the verification of expert knowledge. These best practices can guide educators and instructional designers in successfully integrating AI-driven language models into educational content creation. Here is a combined summary of pages 7 and 8 of the research paper. The incorporation of verifiable references in the first case study serves as a tool for cross-checking the validity of both AI-generated content and subject matter expert (SME) assertions. This approach ensures the creation of robust and reliable AI-generated instructional materials, as SMEs may not possess comprehensive knowledge in all aspects. AI critique, as demonstrated in Figure 3, can augment content quality, but content should be verified with SMEs before incorporation. Furthermore, AI can expedite rubric creation and grading, but educator involvement is crucial for reliability and fairness. In future work, the researchers aim to develop a sophisticated recommendation system that closes the loop in their educational technology solution. A customized version of GPT-4 will be used to extract crucial information from empirical educational studies, encoding data such as educational domain, cognitive load, and learners' prior knowledge into a dedicated database. This database will be used to generate multiple assessment applications for each instructional design principle, guiding users in effectively applying these principles across various educational contexts. The recommendation system is designed to provide evidence-supported instructional design strategies, tailored to the user's specific context, including target learners, learning objectives, subject area, and other pertinent conditions. Each recommended strategy will be paired with example applications and supported by original references from the studies they were drawn from, enabling users to further verify and delve into the source material. The overarching goal is to democratize instructional design expertise, making it widely accessible to instructional designers and teachers, and ultimately driving forward the future of educational technology. This study explores the role of worked examples and problem-solving activities in enhancing learning outcomes, particularly in novice students. The experiment involved two groups, one receiving a combination of 12 worked examples and 12 practice problems, Group A, and another group that was given 24 practice problems, Group B. The results indicate that for novice students, worked examples lead to higher post-test question scores in less instruction time, demonstrating greater instructional efficiency. The paper also discusses the use of data visualization problem-solving activities as part of Case Study 2. These activities are designed to engage students with complex datasets and encourage them to think critically about the information presented. Figures 4 and 5 provide examples of these data visualization problems, which were used for few-shot prompting in the study. In addition to this, the paper references several other studies that investigate different aspects of educational question generation using large language models. For instance, Elkins et al. 2023 examine the usefulness of educational questions generated by large language models, while Prihar et al. 2023 compare different approaches to generating mathematics explanations using these models. Pardos et al. 2023 investigate the learning gain differences between ChatGPT and human tutor-generated algebra hints. Moreover, the paper highlights the importance of scenario-based training and on-the-job support for equitable mentoring, as discussed in Chine et al. 2022. It also mentions the expertise reversal effect and worked examples in tutored problem-solving, as explored by Salden et al. 2010. And the use of anticipatory diagrammatic self-explanation to support learning and performance in early algebra, as studied by Nagashima et al. 2021. Finally, the paper touches upon the concept of instructional complexity and its constraints, as outlined by Codinger et al. 2013, and the potential of prompt programming for large language models, as discussed by Reynolds and McDonnell, 2021. It also references the use of AI chains for transparent and controllable human-AI interaction, as proposed by Wu et al. 2022, and the use of the Vertex AI PaLM API and Python SDK for facilitating these interactions, as detailed by LLC, 2023. The research paper discusses the effectiveness of worked examples for learning outcomes, particularly for inexperienced learners. It highlights the worked example effect, where inexperienced learners benefit from reduced cognitive load, leading to better learning outcomes. In contrast, more experienced learners may not benefit from worked examples due to the redundancy effect, as they already possess the necessary knowledge and skills. The study suggests that the worked examples are more effective for inexperienced learners because they reduce the cognitive overload associated with problem-solving-based learning. This is in line with the findings of Caliaga et al. 2001, which indicate that inexperienced learners may struggle with problem-solving-based approaches due to limited working memory capacity. The paper also presents an example of creating scatter plots using Altair, demonstrating the practical application of the discussed concepts. Overall, the research emphasizes the importance of understanding learner experience and adapting instructional methods accordingly to enhance learning outcomes. In Figure 5, the research presents an example of adding a tooltip in Altair. This figure illustrates how to enhance interactive visualizations by incorporating tooltips that display additional information when hovering over specific parts of the visualization. The tooltip provides context and facilitates a deeper understanding of the data being visualized. On page 14, the paper discusses the implementation of this tooltip feature in Altair. It outlines the process of creating a tooltip layer using the !alt tooltip function, which can be added to an existing chart. The tooltip layer requires specifying the encoding channel and the field from which to extract the tooltip content. The paper also highlights the importance of customizing tooltip content to suit different types of data. For instance, numerical data may require different formatting compared to categorical data. Additionally, the paper emphasizes the role of tooltip placement and styling in enhancing user experience. Furthermore, the paper touches upon the integration of tooltips with other interactive features, such as zooming and panning. This integration enables users to explore the data in more detail and gain insights that might not be immediately apparent from the initial visualization. The use of tooltips in Altair is significant because it enhances the exploratory nature of data visualization. By providing immediate access to detailed information, tooltips allow users to quickly identify trends, outliers, and patterns within the data. This feature is particularly useful in collaborative settings where multiple stakeholders need to understand the data simultaneously. In conclusion, the combination of pages 13 and 14 demonstrates the power of tooltips in enhancing interactive visualizations in Altair. The paper provides a comprehensive guide on how to implement tooltips, customize their content, and integrate them with other interactive features. This contributes to a more engaging and informative data visualization experience, ultimately leading to better insights and decision-making processes.